I will change the schedule here, and I will also put here the dates of the exams, okay? Okay, good. Let's go back to river barrages. And, okay, we were here last time. Just 1 second. Okay, I think it's big enough, more or less. So, we were talking about river barrages in order to withdraw, to take water from a river, and without accumulation, without compensation. So, like when you design a run-of-the-river hydropower plant, so we have 2 options, as I mentioned to you. Either we build a bigger reservoir in order to compensate the mismatch between demand and availability, or we don't build it. And if we don't build a reservoir, we minimize the impact, we minimize the costs, but we don't have compensation in order to, again, compensate the mismatch between water demand and water availability. And therefore we discussed about the structure of a small barrage, which is not automated, meaning that there is no control of the flows. It's completely running alone, without need for control. Even if we said that when we look at the diversion spillways, we said that we put gates there, which are useful in order to regulate the withdrawal and in order to allow cleaning or other maintenance operations. And we said that these gates can be remotely controlled. And nowadays it's becoming more and more diffused, the solution of making the gates remotely controlled so we can manage the diversion without the need of sending people there. And this is, of course, useful. And we already discussed what is the structure here of this type of river engineering work. Now, we had a discussion which was basically qualitative. We didn't go into the details. Today, I would like to close this treatment by discussing some details. And the details that I would like to discuss are those that are related to the hydraulic design. And one first question is related to the elevation of the overall structure, meaning that once that you decide the location and once that you decide the geometry of the structure in terms of the size of these reservoirs, small, not reservoirs, but these traps, gravel traps, sand trap, once that you basically decided the overall framework of the infrastructure, the first question is how to place it along the vertical direction. Of course, the same structure can be put at a low elevation or higher elevation. And if you increase the elevation of the structure, of course you increase the impact on the river. The overall impact, which means that you originate a bigger accumulation of water upstream, because we said that we can tolerate, and in some cases we want some accumulation in order to allow for compensation over short time steps, typically daily compensation. So if we increase the elevation of the structure, of course, it means that also the elevation of the spillways increases, and therefore we originate a bigger accumulation of water, a bigger storage upstream. This is one first type of impact. But also, if we increase the elevation of the structure, we also cause an increased elevation of the water surface upstream during floods. So we increase also the impact in terms of risk of flooding, because of course when you build an infrastructure on a river, you perturb the original, the natural configuration of the river, which is usually something close to equilibrium, and therefore you also have an impact on the risk of flooding. And if the structure is higher, of course, there is a higher increase of water level upstream during floods. Also, when you increase the elevation of the structure, you increase the amount of siltation, meaning settlement of sediments upstream, which means that if after a while you need to clean the upstream riverbed because there was a high accumulation of sediments, of course you may need during these dredging operations to remove a higher volume of material. So the question is, what is the optimal elevation of the overall structure? And this is usually determined by making a refined analysis of the geometry and therefore morphology of the river, and also geology and hydraulic regime. So you need to know basically what is the amount of sediment transport that would be trapped by the barrage. You need to know whether the hill slopes are unstable, because building this kind of infrastructure has also an impact on the stability of the hill slopes. You need to know what is the flood flow, because you need to study the configuration of the water surface during floods with and without the barrage. All of these considerations are listed here. And also, you need to take into account, I already mentioned this, that if you originate an upstream reservoir, which is, as I said, a desirable option, because you have some opportunity to compensate the mismatch between demand and availability. So if you originate a reservoir upstream, you have to take into account that we don't want to go under the jurisdiction, under the competence of the National Authority for Dams. And the law in Italy says that, but this is generally adopted at the international level. In Italy, the law says that if you originate an upstream storage of more than 1 million cubic meters, or if you build a structure that is more than 15 meters high, then you go under the competence of the national authority, which means that the design project should be approved by the national authority, and means that you need to monitor the structure in a very detailed way. So it's something that usually we don't want, because we are talking here about small infrastructures. I talked about a height of 15 meters. It's measured from the foot of the foundation to the highest level where water passes, which is typically the level of the main spillway. We discussed that there is a main spillway, that the purpose of the main spillway is to convey downstream the flood flows. So you measure the height of the infrastructure from the top of the main spillway to the bottom of the foundations. So you don't want to exceed these limitations. And once that you determined, you collected all the required information, of course, you evaluate alternative solutions. Usually we try to keep it at the highest elevation as possible, because we want to use the upstream reservoir. On the other hand, we don't want to increase the flood risk, we don't want to create instability on the hill slopes, and we don't want to go under the competence of the National Authority for Dams. I cannot give a precise law, a deterministic relationship for determining the overall elevation of the structure. What I can say to you is that you have to collect all of these informations. You have also to look at the law in force in the location where you want to build the infrastructure, because usually you have national and regional laws that you have to meet, to respect, and these may prescribe limitations to the impact, which translates into constraints on the elevation of the structure. Once that you determine the overall elevation of the structure, the next question, which is very relevant, is to determine the elevation of the spillways. We talked about 3 spillways: the environmental flow spillway, the diversion spillway, and the main spillway. And these are not placed at the same elevation, of course. These are placed at different elevations. And the lower one, the lowest in terms of elevation spillway, is the environmental flow spillway. Why is that? Because to the lowest spillway you give the priority. Of course, you build the infrastructure and then water starts accumulating upstream, and as water accumulates, you have a raise of the water level upstream. When you reach the level of the lowest spillway, water starts to flow through the spillway. So the lowest spillway is the spillway with the highest priority. And of course we want to give, because the law requires it, we want to give the highest priority to the environmental flow spillway, because before you start taking water, you need to release the environmental flow. So this is the lowest one, which means that your upstream storage increases up to the elevation of the environmental flow spillway. So if you want to determine the upstream storage, you have to take into account that storage increases up to the level of water into the reservoir reaches the level of the environmental flow spillway. So the position of the environmental flow spillway is determined by looking at the volume of water that you want upstream. Of course, if you want more water upstream, you raise the elevation of the environmental flow spillway, which is the lowest spillway. How you determine the storage, the optimal upstream storage? Usually, we look at the compensation that we want to reach between water demand and water availability. And with these small structures, our aim is usually to compensate along 24 hours. Keep in mind that along 24 hours, water availability in rivers usually doesn't change much, unless you are dealing with a river with the presence of a strong contribution from snowmelt or glacier. And therefore, of course, if it is an alpine river, you have an increase of flow during the day in summer and a reduction of flow during the night. If you don't have this control by snowmelt or ice melt, then during the day usually the flow in rivers is not highly varying. The water demand is instead highly varying. So during the day, because of course during the day you have more demand of water in certain hours, and during the night you don't have any demand usually, or very low demand. So during the day, indeed, you may experience some hours where the demand is higher than availability, and hours where availability is higher than demand. So you have to compensate this. And we make a computation of the volume that is necessary to reach compensation, and it's not a subject part of this course how to estimate this volume, but the literature proposes several easy techniques. And once that you know the volume that you need, of course, you place the elevation of the environmental flow spillway. Is it clear so far? Okay, now we have to determine what is the elevation difference between the environmental flow spillway and the next spillway in terms of priority. The next spillway is the diversion spillway. So after we gave priority to the environmental flow spillway, the next priority is for the diversion spillway. And what is the constraint that you have to impose here? The constraint is that you don't take any water, you don't divert any water, as long as you don't release the environmental flow downstream. So you don't take any water if you don't deliver the required environmental flow downstream. So you start releasing the environmental flow. When environmental flow is released, then you can start taking water. Which means that in some periods of the year, you may be not allowed to divert any water, because if you don't have from the river a flow that is at least the required environmental flow, you can't take any water. And this happens usually when we build, for instance, hydropower plants, run-of-the-river hydropower plants. We have periods in the year where we can't run the plant. First question, how to determine the environmental flow? It is usually dictated by regional laws. In Italy, it is dictated by regional laws. So you have to go to local administrations in Italy and ask information. Usually they give you an empirical relationship to compute the environmental flow. It's very easy. We don't discuss on it because these relationships are, as I said, empirical. It's useless to learn them by memory, because the laws that are applied, for instance, in this region, which is the Emilia-Romagna region, it's not the same law that is used in Tuscany. They have different laws. At the end of the story, the result is more or less the same. I think that I already gave you an order of magnitude. The order of magnitude is, if you look at the flow duration curve, is the Q355. Namely, the river flow with a duration of 355 days. And this is an empirical rule that was used in Switzerland up to 15 years ago. They just said the environmental flow is equal to the Q355. And it is basically the same result that we expect from the regional empirical laws. Okay, this I didn't discuss so far, this relationship. I'm getting more or less there now. So, once that you determine the environmental flow, and then the question is, so let's suppose that you have this structure, which is done in this way, more or less. And this is the river bed. And let's suppose that you placed your environmental flow spillway here. So this is the ENV flow. Now the question is, at what elevation should I put the diversion spillway? Let me depict the diversion spillway here in this way. Let's suppose that this is the wall, the side wall of the structure. Side wall. And in the side wall, you may have here the diversion spillway with a gate, possibly. Usually there is a gate here which goes up and down along a screw. And here you have diversion, the diversion speedway. Diversion speedway. And this is the main speedway. So the question is how to determine the elevation difference, which is called here, I think, delta H1. How to determine the delta H1, which is the elevation difference between the environmental flow and the diversion flow and the diversion speedway. And then there is another elevation difference, which is delta, probably you don't see anything here, so let me show it here, delta H2. So we have to determine this, everybody can see here, I hope so. We have to determine the two elevation differences, delta H1 between the environmental flow speedway and the diversion speedway, and then we have to determine the difference, elevation difference delta H2 between the diversion speedway and the main speedway. Okay, so how to determine them? So let's indicate with the symbol QP the environmental flow. So the environmental flow is given by QP. It's QP, or let me see, because I'm not sure if I'm using the same. So, no, QP here is the design flow. Sorry. Design flow, which is the diverted flow. So design diverted flow. Let me write again. Design diverted flow, QB. And I don't remember what is the symbol that, okay, QDMV. Environmental flow. Is QDMV. I use DMV because DMV it's the acronym for the flusso minimo vitale in Italy. So in Italy it's called, usually the environmental flow is called DMV. And let me also, in order to reach consistency with the slides, I need to invert the 1 and 2 subscripts here. So I need to call with the symbol delta H1 the elevation difference between main speedway and diversion speedway, and with delta H2 the elevation difference between diversion speedway and environmental flow speedway. This is just to reach consistency with what is projected there. So the question is now, what is the elevation difference, delta H1, and how can we determine it? So, there is one first thing that you need to take into account. In order to compute the flow through a spillway, there is a relationship which is given by fluid mechanics, by the fluid mechanics theory. And this relationship says that the flow is controlled by the geometry of the spillway and the water head above the spillway, the water height or hydraulic head above the spillway. Again, in order to compute the flow through a spillway, we need to use a relationship that is given by fluid mechanics, which is already projected there. I will write it on the blackboard. And the flow is controlled by the geometry of the spillway, first, and second, which is fixed, the geometry of the spillway is fixed. Second, the flow is controlled by the water height over the spillway, which is also more or less equivalent to the hydraulic head, which is hydraulic energy of the flow. So this relationship reads let's now focus on the diversion spillway. So let's now compute the flow through the diversion spillway. This relationship reads QP is equal to a coefficient μ, which is a flow coefficient. And then there is the width of the spillway, LP, the width, I'm just checking that here. And then there is the hydraulic head, delta H1, which is, again, it's better to call it the water height over the spillway, which multiplies the square root of 2g, again, delta H1 So you can write this relationship in this way. If you want, QP is equal to μ LP delta H1 to the power of 3/2 times 2g at the power of 0.5. Me, for this kind of infrastructures, is usually taken equal to 0.385, which is valid for spillways with a long threshold, which is the case of these spillways usually. So if the spillway has a long, in the longitudinal direction, threshold, the coefficient is equal to 0.385. If the spillway has a very short, very thin threshold, then the coefficient increases. But let's assume that we have a long threshold. Actually, usually it happens that you have long threshold in the main spillway and environmental flow spillways, because you see that the threshold is very long, because you need to pass the structure. So it's indeed a long threshold. For the diversion spillway, usually the threshold is very thin. You understand the meaning of the threshold, what is? It's basically the part of the spillway where the water passes over. So usually for the diversion spillway, we use a very thin threshold, and therefore the coefficient increases, which is also nice because it increases the efficiency of the spillway. Okay, so from this relationship here, you see that you can get an explicit representation, an explicit formula for delta H1. So if you equate the flow, if you equate it to the design diverted flow, you get a value for delta H1, which is precisely the water height that allows you to divert the flow QP, the design flow. So when you reach over the diversion spillway that water height, you are done. You can allow the extra water coming from the river to flow through the main spillway downstream. So this is why I put this water height over the spillway corresponding to the flow QP, I put it equal to delta H1, which is the elevation difference between the diversion spillway and the main spillway. So you get water that starts flowing to the diversion, and if you get an increasing water height, you have an increase of the diverted flow. When the water height reaches the level over the spillway of delta H1, you are done with the diversion. You don't want more water because can't use it, and therefore you place the elevation of the main spillway at that level, because the excess water you want it to go downstream. Is this clear? Okay. In analogous reasoning, the very same reasoning allows you to determine the elevation difference between the environmental flow spillway and the diversion spillway, which is delta H2. And the only substitution, you use the same relationship by substituting QP with QDMU and substituting delta H1 with delta H2. Sorry if I'm crossing. I have a small blackboard, please.
LP is the width of the spillway?
It's the width, and therefore here you are correct. You have to substitute LP with LDMV. And in fact, if you go down in my slides, in my web page, you see that there is, okay, here instead of LDMV, I used LC. Sorry for that. It's not fully consistent with what I wrote here, but you see that indeed now we are talking about delta H2 and we are talking about QDMV. So this is the first question that we had to reply, how to place the elevations of these spillways. And the answer is by looking at the amount of storage that we want upstream, by looking at the overall configuration of the riverbed plus the infrastructure, and by looking at the geometry of the spillways and related flows. Needless to say, when we talk about the diversion spillway, you may have 2 or 3 of them. This is usually done. Usually, instead of one large spillway, we prefer to have 3 smaller spillways. Why is that? Because it's easier to regulate the flow through them. It's easier. And also, you know, when you have 3 gates instead of 1, you have a more resilient solution. Because, you know, if you have just 1 gate, if the gate breaks, then you can't use anything here. If you have 3 gates, if one of them gets broken, you can still regulate with the other 2 gates. This is why, for instance, when we build an hydropower plant, instead of a big turbine, we prefer to have 2 smaller turbines, because if one breaks, I can still use the other one. Or when we have a pumping station, we prefer 3 pumps instead of 1 big pump, the same reason. And even here, usually we have 3 gates or 2 gates. Needless to say, in this case, LP is the total width of the gates. So you sum, if you have 3 gates, you sum the width of the 3 gates. Okay. Next question, how to design I go back to the sketch. How to design the sand trap and the gravel trap. It's an hydraulic design, because the problem that we have is that when we divert water, together with the water, we divert sediments. And the problem is more relevant when you have high flows. In fact, usually when we have flood flows, so when the river flow exceeds a given threshold that we determine basically empirically, we stop the diversion, we interrupt it. Why is that? Because when the flow is very high, we have a lot of bed load, sediment transport, and we don't want to divert water with a lot of turbidity and a lot of mud in it and a lot of sediments. We don't want that. because usually when we take water, we want clean water, unless there are very specific type of uses where we can tolerate water that is not very clean, but in 99% of the cases we want clean water. And therefore, clean water means that we don't want floating material, we don't want turbidity, and we don't want sediment transport in it. Think, for instance, at a turbine. If you turbine water that has some gravel in it, of course it may run the risk of breaking the turbine. And usually the producer fixes limits to the diameter of the sediments that the turbine can tolerate. So if you look at the technical details of the machinery, usually you see what is the amount of sediment or the amount of turbidity that the machine can tolerate. And if you provide water to an aqueduct, you have laws in force that limit the concentration of certain substances, like turbidity. It's limited by law. And therefore, usually you have prescriptions given by the producer or given by the law in force that limit the amount of material that you can bring downstream through the diversion. So this is why usually when we have flows that passes a given threshold, we stop the diversion. But in any case, even if we divert water when the river flow is quite low, we have sediment transport in it and we need to remove it. So this is why we place a gravel trap and a sand trap. And we usually place the gravel trap first, because, of course, the sediment that first settles down is the sediment of greater size. And therefore, we first remove the gravel and then we remove the sand. And usually the gravel trap and the sand are like two small tanks, two small storages. The sand trap usually is bigger than the gravel trap in terms of